Had a request to go over this problem, 20.52. And this question is looking at an electric dipole. And the way the dipole is set up is the same way that the book sets it up. So it has your XY axis, kind of like this. And then they put the positive charge here and the negative charge here. And these are at points, this is at point x equals to positive A. And this is the point x equals to negative A. And what they want is they want to find the electric field at some random point x. And so the way we do this is, we handle electric field from a point charge, is we use this equation right here. Okay, so this is our magnitude, and we're going to add this up for 2 point charges. And so we got a positive charge and a negative charge. And so if you look right here at this point, you're going to have the electric field from the positive charge is going to be in the positive x direction, and then the electric field from the negative charge is going to be in the negative x direction, just like we would expect. And so if I write out the E total, so as the E total, this is all going to be in the x direction. That's what's really nice, or a little bit easier about this one, is that there's no angles you got to use here. And so if I take my equation, let's just add this up. Let's do the positive one first. So it's KQ. Now in these examples, they just give you some choose. So this is like negative Q, and this is called positive Q. So it's KQ, and now I got to do the r squared part. And so here's where you got to look. So if my x is measured from the origin here, and so the distance to the positive charge is going to be this x all the way down to the origin plus an extra a. So it's going to be x plus a squared. Now the same thing for the negative charge. And now if I look at that, the distance between the negative charge and my point is just right here. And so if I look on my diagram, I would call that x minus a. So it's a little bit smaller than x. And so this distance is a little bit bigger than x. This is a little bit smaller than x. And so I get x minus a squared. Now, the physics is sort of done here. Okay, so we've got this. This is adding this up. The rest of it is sort of manipulating this mathematically to get the answer that they're looking for. And depending on the problem, they can ask for different kinds of things. But we're going to sort of show you how to go about doing that. Now, what they want you to find out here is they want you to find what this equation equals when x is much, much bigger than a. So that's a real common thing because typically when you're dealing with a dipole, you're pretty far away from it. Now, the problem with that is if we just go down here and assume a is less than x and get rid of it, this thing equals 0. Okay, so sort of we're doing our first approach doesn't really help. And so what can be useful here is to take these two things and add them up and to get a common denominator. So the way I would do that is I would write it kind of like this. So it's KQ. Now down here, the easiest way to make a common denominator is to go x plus a squared and then x minus a squared. And so I have to multiply up on top on x minus a squared. And then for this guy, it's going to be similar but the opposite. So to get this same common denominator of x plus a squared, x minus a squared, up on top here I got to multiply by x plus a squared. And so all together, when I finish with this, I can add them up kind of like this here. And so I'll have KQ x minus a squared minus KQ x plus a squared. So now this is still an exact equation. Okay, so this is still equal to this thing here. We just sort of written it in a different form. Okay, and so we're still dealing with the exact equation, but now we want to look at this a little bit closer. And if I take these pieces and expand out the a plus x squared and the a minus x squared, okay, this will come out to equal something kind of like this. So I'll have the same common denominator downstairs. And then upstairs, you'll find that there's a lot of things that cancel out. And what gets left over is there'll be a 4kq a times x. So again, that's by expanding that out here. Okay, and so it's really important to go through and do that, but now you have this. And so the final step is I'm going to make this approximation that x is much, much bigger than a. So if that's true, I can essentially cancel out these two a's here. And so in my new equation, I have x squared times x squared. If I get those out, it's just x squared, which is, of course, is x to the fourth. But let's just write it that way for now. And then on the top part, I get 4k q ax. And so what happens is one of the factors of x cancels with the one upstairs. And so I'm left with 4kqa over x to the third, which is getting closer to what they were looking for. And then just the final step is this definition, which I'll probably never use, but they like to use this. And this is just a definition of the dipole moment. The magnitude of the dipole moment equals the charge times the distance of separation. And so for us here, that would be 2q times a, since our d equals 2a. Remember that the dipoles are at negative a and positive a, so the total separation between the dipoles would be 2a. And so if I take that here, that gives me back 2, because I use one of the 2's in here to make that 2q times a. So I can write 2 times k, and then I'll have a 2qa left over, which is just the same thing as that p, that's just their definition, over x cubed. And so I get exactly what they're looking for there. And of course, we remember that this is in the positive x direction. So the idea here is, again, the first step is we do like we're doing our physics. We use this equation to find the electric fields. And then if they want this x bigger than a, there's different ways to do it, but probably the easiest, I think, is to go ahead and add up these two terms like that. And then once you add them up, then you can go down here and at some point do the part where you sort of cross out the a's. Okay, so ask some more questions if you're still got some questions on this one. Thanks.